Hello, hi everyone. Next, we are moving to the lecture number 2, rectifiers. Okay, so in this particular case, already rectifier converts alternating current into direct current. So in this particular case, it converts alternating current into direct currents. We have a different type of rectifiers we have. In that, the first rectifier is a half-wave rectifier. Okay, that means that in the AC signal, in the AC signal we have a positive half cycle as well as negative half cycle. In the positive half cycle only it transfers to the output, negative half cycle is clipping. So only one half cycle is transferred, either positive or negative. The second one, full wave rectifier. Full wave rectifier. Okay, this is the second case. Third one, full wave bridge rectifier. And then full wave center damped rectifier. Okay, so these are the rectifiers mentioned in your syllabus. Of course, so many rectifiers we have: single phase rectifier and three phase rectifier. In a single phase rectifier, we have classified into half wave rectifier and then full wave rectifier. In the full wave rectifier, again classified into full wave bridge rectifier and uh, full wave center tap rectifier. Again, single three phase rectifier, half wave rectifier, full wave rectifier, and again full wave rectifier classified into full wave bridge rectifier, full wave center tap rectifier. All these things are not required for that moment. Okay, these are the four things are required at the examination point of view, because it is clearly mentioned these four rectifiers in your syllabus. Clear? So let us move to the first one, single phase of a rectifier. Single phase of a rectifier. Let us see the working in the brief manner, then I will give the formulas, and then in the examination point of view we will discuss the one or two problems based on the single phase of a rectifier. So in this particular case, I won't provide any derivations in this particular class, because we are preparing for the competitive examination. So we have only 10 days left hardly. So if you are doing derivations and remaining things, our time going to be wasted. What is required exactly, those points I am going to explain. Okay, so the case here of a rectifier, the working first we'll see how exactly it is working. So in the positive half cycle, if you are connected, this is a positive half cycle of the waveform, input waveform. This is a positive half cycle. In this positive half cycle, it is a positive, it is a negative. Okay, whenever anode is connected to diode, anode and cathode, and whenever anode is connected to positive, cathode is connected to this particular negative terminal connected here, cathode is connected to negative. So diode D1 is forward bias, that is a D is a on state, it is a forward bias. So for example, it is ideal cases I am going to discuss. At the 0 volt only diode is conducting. That means that our equivalent circuit diagram will be, this is the diode, it is on state, as well as here resistor RL is present. After that, we have a supply is given, positive and negative of cycles here. Okay, this is the equivalent circuit diagram. Now the current flowing through this circuit will be IL, right? The voltage across between output terminals is VL, that is the output voltage. Okay, now in this particular case, the output voltage, what about you are giving the input voltage, the positive half cycle, right? Same positive half cycle is appears here, because total entire thing is parallel to the input. There is no in between resistors or remaining thing. That means positive half cycle present here. That's what here positive half cycle is present. Clear? This is the voltage. This is the positive half cycle waveform. That is enough working. Next, coming to the negative half cycle. It is a positive half cycle. Half cycle. Next, we are moving to the negative half cycle. Okay, negative half cycle. In the negative half cycle, look at here. While you are given this negative input to here, these terminals are negative and positive. Anode is connected to negative and this particular cathode is connected to positive. What will happen? Diode is reverse bias. So D is off state. Okay, whenever D is off state, we are going to draw the equivalent circuit. The input voltage here connected negative, diode is off state. Okay, D is off state, and then this is the load we are connected. Now my question here, whenever it is open circuited, whatever the current flowing through the load is equal to 0. So this is the RL, load resistance. So what about the voltage across the load will also 0 because there is no current flowing here. So there is no current flowing here, voltage is also 0. So finally, what about the negative output? This particular waveform negative output is completely 0. So output voltage completely 0. So this is the waveform is repeated in the next half cycle. Output is present, and then negative half cycle output is equal to 0. This is all about half-wave rectifier. Clear? So in this particular rectifier case, we will discuss the different parameters. The first parameter we are going to discuss about the average value. So the first parameter in the examination point of view, you should remember all these points what I am giving to you. So first one is average value. In the second chapter, the second or third unit, I gave the AC fundamentals, average value, RMS value, everything, right? From that I am going to derive that average value. So the average value of the half-wave rectifier waveform will be, whatever the output you got. First we will draw the output waveform V0. This is a positive half cycle. This is a positive half cycle. Negative half cycle is 0. That means here the average value of this total entire thing, if you make it average, then you will get this particular thing. That is called as a VDC. Okay, average value. So in that case, the average value VDC formula, already mentioned, I won't give any derivations here, just I will provide the formulas to you. So Vm divided by pi. Okay, so what it is also, write it as a 0.318 Vm, where Vm is a maximum value. In that particular case, here Vm is a maximum value. Okay, so this is about the VDC. Next, average value of voltage. Next, average value of current, IDC is equal to current, voltage, load resistance, RL value. From that, current I is equal to V by R, VDC divided by RL. That means that VDC is nothing but a Vm divided by pi into RL. So that will be equivalent to 0.318 Vm divided by RL is a formula. Another formula in terms of Vm maximum value. In terms of RMS value is given, the formula will be 0.38 into root 2, right? 0.45 V by RL. This is another formula in terms of V. In this particular case is a RMS value. If here it is mentioned RMS value, this is the formula. Okay. In the examination, you know the maximum value using this formula. You know RMS value it is given directly. We are using this formula. Of course, you can multiply 0.38 into root 2. In the examination, time is consuming, right? That's why can use that. After that, you know RMS value. IRMS is equal to IM by 2. It is a half wave rectifier. It is a IM by 2, that will be equivalent to 0.5 IM. In the case of similarly voltage is also VRMS. With the same formula, VRMS is equal to 0.5 V. 0.5 VM, the maximum value. So that's what we are the RMS value as well as maximum value cases. Next we are moving to the second parameter. We have to remember the peak value, otherwise peak factor. So second one, B. P form factor first we will discuss. Form factor. It is also very important. Directly they will ask the questions. So form factor, you know, it is a ratio of RMS value divided by average value. So that will be F is equal to RMS value divided by average value. So what is the RMS value you got? You know, 0. You will take in terms of current 0.15 IM divided by what is the average value in terms of current 0.318 IM, right? That is a RMS value. So from that IM will get cancelled. So form factor will get 1.57, that is for sinusoidal waveform in case of half wave, AC waveform, AC wave. So the form factor, you know, in general the form factor for alternating current or alternating voltage 1.11, but here the waveform is not alternating. The waveform is half wave rectifier, only positive half cycle is present. That's why you got 1.57. In general for alternating waveform it is a 1.11. Okay, but it is a waveform of half wave, that's why it is a 1.57. So everyone is clear about the form factor, right? Then we are moving to the second one, third one, peak inverse voltage. It is also important. PIV, it is called as a peak inverse voltage. What is a peak inverse voltage? We'll see first. So the peak inverse voltage is nothing but the maximum voltage. The peak inverse voltage is nothing but the maximum voltage across the diode, the maximum voltage across the diode in the reverse direction. So in this particular case, what is a maximum reverse peak inverse voltage? We'll see. The peak inverse voltage already mentioned, the maximum voltage across the diode in the reverse direction. So reverse direction, that is nothing but in the reverse bias condition. What is the maximum voltage? So we are giving some Vm, right? The V or Vm, maximum voltage is Vm. That is a negative Vm you are giving, because it is a negative Vm. So minus Vm is given, that will be appears across this particular circuit. Now whenever it is open circuited, current is equal to 0. Of course it is a valid. but voltage is present, that voltage is a Vm, negative Vm. Got my point? What is the peak inverse voltage now? The peak inverse voltage will be Vm. So the peak inverse voltage in the half-wave rectifier, so V peak inverse voltage VPIV is equal to Vm. That is a peak inverse voltage. Okay, that is also important point. After that, ripple factor. Next important point we have to remember, ripple factor. Okay, so ripple factor is a very simple thing. So ripple factor nothing but a in case of rectified output, some pulses present, some spikes will be present in the waveform. The spikes we are called as a ripples. So in this particular waveform, the ripples are also how much of ripple present we will discuss now. For half-wave rectifier, the ripple factor is equal to gamma. It is represented for ripple factor. That will be the ratio of RMS voltage or RMS current divided by average voltage or average current. What is the RMS value of voltage? You got 0.385 for half-wave rectifier into Vm. VDC 0.318 Vm. So this is the RMS value, this is the average value you got. From that both are get cancelled, you will get 1.21. So everyone remember that the ripple factor for half-wave rectifier is 1.21. Okay, the relation between Vm and DC is given. You know the relation between Vm and VDC. The relation between Vm and VDC is equal to Vm divided by maximum value divided by DC value, that is average value, is equal to, in terms of 1.3 gamma. It is also, remember that. Maybe directly they will ask the question. It is important. Okay, that is about ripple factor. Then we are moving to the next important formula, that is the efficiency. So efficiency of a half-wave rectifier, we'll see. The efficiency is nothing but a output divided by input. That is called as a efficiency. So once you derived everything, the efficiency you will get, the formula directly I will provide it to you. ID square into RL, that is output, divided by input is I RMS. Input is AC, right? IRMS into diode resistance, forward resistance plus load resistance into 100. So from that, you know, I will substitute the IDC value, IRMS value from the previous cases. Directly I will get 40.6 divided by 1 plus RD divided by RL. If I am neglecting RD, when I am neglecting RD, what will happen? Total entire term is neglected. Finally 40.6% is a percentage. 40.6 is a efficiency of a rectifier. Still these are the formulas we have to remember. This is enough for the examination point of view in the half-wave rectifier case. I hope that everyone is clear. Next we are moving to the one problem related to that. Then we are moving to the next full-wave rectifier concept. A single phase half-wave rectifier supplies power of 1 kilowatt load. So you know half-wave rectifier, it is able to supply the power of 1 kilo ohm load. The input supply voltage is 200, that is RMS value it is given. Neglecting the forward resistance of a diode, calculate the VDC, IDC and ripple voltages. 3 points you need to calculate. So first one, A. The first point, VDC, that is nothing but average value. What is the formula for average value if it is given RMS 0.45 into V? Okay, this is the RMS value is given. So 0.45 into 200, that will be equivalent to 90 volt. Okay. Second bit IDC, that is a current. VDC divided by RL. What is a VDC? Is 90. RL is a 1K. That will be equivalent to 90 milliamperes you got. Okay. After that, ripple factor. Ripple factor is nothing but a VRMS divided by VDC. What is a VRMS by VDC? So you want ripple voltage in terms of RMS value. Okay. So we'll do one thing. In case of half-wave rectifier, what is the ripple factor? 1.21 is equal to VRMS. VRMS you want. It is a multiply with VDC in this particular side. From that, VRMS is equal to ripple factor 1.21 divided by 100. That is a factor in terms of percentage we are taking into VDC. VDC is equal to 90. So we will get 1.09 volt. So why I am multiplying 100? Because the factor what we got exactly is 0.0121. After that we are multiplying with 100, then we are mentioned 1.21. That's why in the multiplication of actual figure we can divide it by 100. So that is about the RMS value of ripple voltage 1.09 volt. This is about the problem. Okay. Next we are moving to the single phase full wave rectifier. So full wave rectifier, this is the center tap. Okay. The center tap is nothing but the transformer of a secondary winding tapped exactly center middle of the secondary winding, and then load is connected in between them. Okay, here how many diodes are present? 2 diodes are present. So what the output waveform you expected, we'll see one by one. So now in this particular case, we have a two cycles working. We are going to see the first case is a positive off cycle. Positive off cycle. In the positive off cycle, our circuit diagram will be, the equivalent circuit diagram will be, if you are giving the voltage to the circuit, so it is a positive, okay, it is a negative. That means that with D1 is a forward bias because anode is connected here and cathode is connected here. Here anode and cathode. Negative terminal connected to anode, it is a reverse bias. Positive terminal connected to anode, it is a forward bias. That means that in this particular case, D1 is conducting, it is a on state, and then here in between we are connected to the supply, the middle of resistor, here transformer winding is present. In between resistive load is connected, that is RL. What about the output side here? In the second part of the circuit, D2 is a off state. So this is about the equivalent circuit if you are providing the Vs input voltage here. Now my question here, the current will be passing from here, the same current will be entering this direction. This is the current direction. Okay. Now what about the current here? 0. The current will be 0. There is no current flowing. So what about the voltage? The voltage available, total voltage is Vs. This is a Vm. This is also Vm. two parts here. So how much voltage present in the first case? Vm only. Okay, Vm is present voltage across the diode. So next, coming to the waveforms, how exactly the waveforms will be. So the waveform will be input we are providing positive half cycle, output is also will get. So input we are providing positive half cycle, output is also will get. Okay, output is a positive half cycle. This is a case of positive half cycle. Then we are moving to the negative half cycle. Negative half cycle. In the negative half cycle, the same thing is repeated. Look at here. RL. Okay. So in the negative half cycle, what will happen? So this negative terminal is connected to the negative half cycle. The polarities will be negative and positive. Okay, in the negative half cycle, this negative terminal is connected to anode, and this positive terminal connected in this below figure. It is a anode positive terminal. That means that D2 is a forward bias, D1 is a reverse bias. So D1 is a reverse bias means it is a open circuited. D2 is a forward bias means that it is a on switch. Clear? Right. Now my question is, what is the current direction? It is important. It is a positive, it is a negative. The current will be flowing from always positive terminal, and then current entering that direction will be, this is the direction. What is the previous current entering direction? Same direction. So current direction is same. What about the voltage we are providing? The same polarity of voltage here also. The polarity of voltage here also, polarity of voltage, both the polarities are same. Even though we are connected negative half cycle, you will get positive output only. Got my point? This is a rectification. So the positive half cycle converted into positive half cycle, negative half cycle is converted into positive half cycle. That's why both are positive half cycles only. Then finally, the waveforms will be the input here given. This is the input voltage. So look at here. This is the output waveform. It's a positive half cycle. Negative half cycle is converted into positive half cycle. This is a full wave rectifier for bridge type circuit. So we'll see the formulas related to this particular case. The first one, average value. So average value we'll see. The average value for full wave rectifier is equal to VDC. That is in case of voltage, VDC is equal to 2 Vm. Previously it is a Vm only, but here full wave, right? 2 Vm divided by 5. That will be equivalent to 0.636 Vm. Okay. It is a twice of half-wave rectifier. This value is a twice of half-wave rectifier. Half-wave rectifier. Next, second thing, that value will be 2 into, what is a Vm? Can also write it as a root 2 Vrms. Yes or no? Divided by 5. That will be in terms of, if it is Vrms value is mentioned, 0.9 Vrms. Directly we can use this formula. In the examination, they will provide the maximum value. We can take it maximum value. This is the formula. If it is provide RMS value in the examination, so you can take this formula 0.9 into Vrms. So the same thing is repeated for current also. So the current case, IDC, we can take. IDC is equal to 2 Im divided by 5. That value will be 0.636 Im. In the same case, current 2 into root 2, okay, 2 into root 2 divided by pi into Im is equal to 0.9 IRMS. Right. This is about the another formula. If you are in case of you are using directly in the examination, that also write it as a 0.9 into VRMS divided by load resistance. This also you can use it. So different possibilities like that only. Next we are moving to the RMS value. In second B is a RMS value. So RMS value for full wave rectifier, it will be same as AC, in the case of previously, 0.707 IM RMS value. That means IM by root 2 actually RMS value. IRMS. Similarly, VRMS also same thing, 0.707 VM. Next, third one, C, PIV. Already mentioned. What is mean by PIV? Peak inverse voltage for when our diode is reverse bias. So we'll discuss what is a peak inverse voltage. PIV is equal to. Very important in the examination. I guess 2015 paper they asked this particular question. So what exactly we'll see. So the peak inverse voltage, whenever okay. So in the case of D2 or D1, we can analysis the output, the open circuit voltage. Here V1, VM as well as here VM is present. The open circuit voltage when a diode is reverse bias, both the diodes are reverse bias, VM plus VM, 2 VM is present. Okay, that is the case in case of bridge rectifier. It is a speciality. 2 VM is equal to 2 VM, 2 times of peak inverse voltage, because your center taper transformer we are using, that's why you got that. So finally peak inverse voltage is equal to 2 VM. Coming to the ripple factor, that is represented by gamma, ripple factor. Okay, so gamma is equal to, ripple factor is equal to VRMS divided by VDC. You know that. So what about the VRMS? 0.305 VM by 0.636 VM. VM get cancelled. You will get 0.482. So this particular ripple factor is less than the ripple factor, because the output waveform present both the cycles, right? Positive and negative of cycle. The relation, okay, the relation between VM and VDC is the same relation in the previously what I gave. So you can write those relation directly here. So that will be VM by VDC is equal to 1 plus root 3 into gamma. That is the relation between VM and VDC. Okay. Next we are moving further. That is the efficiency at the last. So C, efficiency. So already mentioned, efficiency is nothing but a output divided by input, that is the efficiency. So what is the output? ID square into RL divided by output divided by input, IRMS square into RD plus RL. So finally, if you are substituting this RMS and IDC value here, you will get this relation, 81.2% of 1 plus RD divided by RL. I can neglect RD. When I am neglecting RD, So finally I got the efficiency is a 81.2%. This is important in the examination. What is the efficiency of full wave rectifier? 81.2%. What is the efficiency of off wave rectifier? 40.6. Exactly, double the efficiency of off wave rectifier. Clear? Then we are moving to the one problem. Then we are going to discuss about the full wave bridge rectifier. Okay, right. In the case of full wave rectifier, what they are providing, the load is 1 kilo ohm. AC voltage applied to the diode 200 to 200 RMS. That is a peak to peak voltage. 200 in the one part, 200 in the second part. So if diode resistance is neglected, calculate average value of DC voltage, average value of DC current, and then ripple voltage. These three things we are going to calculate. So now the first thing, VDC. If it is provided RMS value, the formula gave 0.9 VRMS. What is a VRMS? 0.9 into 200. That will be equivalent to 180 volt. Okay. Next, second, average value of DC. That is IDC is equal to, again VDC divided by RL. What is a VDC? Got 180. RL is a 1K. That will be 180 milliamperes. Third one, C. VRMS of ripple voltage. That will be ripple factor into VDC by ripple factor divided by 100. So what is the ripple factor? 0.482 divided by 100 into VDC is 180. You will get 0.868 volt. So this is about the full wave rectifier case. Next we are moving to the next topic is a single phase full wave rectifier bridge type. Okay, bridge type full wave rectifier. So in this particular case, bridge type full wave rectifier, again we are connected, the transformer is connected to 4 diodes. In the previously, how many diodes are there? 2 diodes are present, but here 4 diodes are present. We'll see what exactly the working principle in the positive off cycle and negative off cycle. Positive off cycle. In the positive off cycle, the diode will look at the polarities positive and negative. So I will use another color. See here, this positive terminal is connected here. This positive terminal connected here. Coming to this negative terminal is connected here. This negative terminal is connected here. Okay, got my point. That means here this particular D4 is reverse bias as well as D2 is a reverse bias. So D4 comma D2 are off state. Got my point. Next, D1 and then D3 are on state. That is a forward bias. So whenever D1 on, D3 on, and D4 and D2 is off state, our equivalent circuit diagram will be these 2 diodes are get cancelled. Only the current, I will show this equivalent circuit diagram below. Now see, D1 is on state, it is a closed switch. Next, this particular diode is off state. Next, D3, that is a D3, D1 is here, D4 and D2. Okay, clear? Next, load is connected in between them. So load is connected in between these two terminals, right? This is the load resistance. Now this is the output is input is connected here. So the input which waveform is connected, positive waveform is connected. Now identify the current directions. So the current will be flowing like that. So again it is a open circuited current will be 0 amperes. Now it is current is flowing. That current will be flowing through the load. This is the direction. This is a voltage VL. Okay, this is the direction is entering, and then this is the direction. Again this is the direction, and it is entering into the negative terminal. It's starting from here and entering to the negative terminal. It is a closed path, right? So in this particular case, the what about the value are given positive half cycle, the output is also present positive half cycle only. Okay, just that's what here represented. Here given positive half cycle, we will get positive half cycle only output. Okay, this is a diode in the diode D1 and D3 values. Coming to the D2 and D4 values. In the D2 and D4 both are open circuited. Whenever both are open circuited, what about the output in the positive half cycle? 0. There is no output. Next, coming to the second case, negative half cycle. Negative half cycle. In the negative half cycle, we will draw the diagram. This is a diode. In the negative half cycle, look at here. Negative half cycle means we'll take another color. This is a negative, this one is a positive. Coming to here, this negative terminal connected here, this negative terminal connected here, this, okay. Next, this positive terminal is connected here, this particular positive terminal connected here. Okay, that means that here D1 and D3 are off state. D1 comma D3 are off state, and D4 comma D2 are on state. So you know, in this particular case, particular D1 is off state. Next, coming to here, D4 is on state and D3 is off state. In between, D2 is on state. Now the load will be connected in between these two terminals. Okay. So load is connected in between these two terminals. This is the load resistance RL. So after that, the input here connected. This is a negative half cycle we are giving to the input. Fine. Now the current direction will be in the negative half cycle. This is the current direction is flowing. It is trying to flow this direction, but it is the diode is open circuited. Current will be 0. Now this is the direction of current, and look at here, the direction of current, the polarity will be the same as previous polarity. That means that even though your negative half cycle is given, it is converted into positive half cycle. Okay, then this is the direction, this is the direction, and then this is the direction, and it is entering to this here. This is a negative terminal, positive, right? It is a positive terminal, it is a negative terminal. This is about negative half cycle for the full wave rectifier. Look at here the waveform. The negative half cycle, this is the waveform we have. Output is present for the D2 and D4. Here output is 0. I combine both, I will get the output is full wave rectifier. This is the actual output. Okay, this is the actual output we have. So finally you got the idea about the full wave rectifier also. Then we will look at the one by one for average value, RMS value, form factor and peak factor values one by one. The first one, average value. So average value is equal to the VDC, first in terms of voltage. VDC is equal to 0.636 VM. That is a, in terms of RMS value 0.9 VRMS. You should remember that. Okay, next second case, IDC, average value. IDC is the same as 0.360 IM. IM is nothing but a VM by RL. That is also write it as a 0.9 VRMS divided by RL. After that, RMS value. RMS value IRMS is equal to 0.707 IM. All the formulas are same. What formulas are present in the bridge center tap rectifier, the same formulas are repeated here. So next, form factor. Form factor is equal to 1.11. Coming to the peak inverse voltage, PIV. So the peak inverse voltage of a diode, PIV. Here peak inverse voltage is different from the previous case. It is in the previous case the peak inverse voltage is VM, but the peak inverse voltage here, each and every time only one VM is present, because here there is no center tap transformer. That's why here the VM value, the peak inverse voltage is the VM. So this is the only difference between bridge rectifier and this full wave rectifier. Okay, in case of bridge rectifier, peak inverse voltage is equal to maximum voltage. In case of center tap rectifier, peak inverse voltage is 2 times of maximum value. Okay, next, coming to the D bit, ripple factor. Ripple factor, that is gamma, is equal to it. Directly I am giving 0.482. 482 is the ripple factor. Remaining everything is same for previous and this particular case. So ripple factor is equal to 0.482. So finally, last one, efficiency. So efficiency is same as the previous case. So efficiency is equal to 81.2%. Why I am not writing everything? Because everything is same except peak inverse voltage. So this is about the efficiency cases. So finally we completed the rectifier concept completely. So we'll look at some advantages of rectifiers. So bridge rectifier, advantage compared to off-wave rectifier. So we will look at into advantages of full wave rectifier. So the first advantage is here. In case of bridge rectifier compared to center tap, there is no center tap transformer. No center tap transformer is required. Transformer is required. Okay, in case of bridge rectifier. Next, second, much smaller transformer are required. Much smaller transformer is required compared to center tap rectifier, center tap bridge full wave rectifier. It is suitable for high voltage applications. So it is suitable for high voltage applications. Okay, next, fourth one, it has a less PIV rating per diode. It has less PIV. PIV means that peak inverse voltage rating per diode. Then you will get the doubt, sir, this peak inverse voltage should be more or less. This peak inverse voltage will be less. It is easy to design the particular diode. Okay, peak inverse voltage. So that's why advantages only. If it is less, it is advantage. In case of center tap, it is a 2 vm. That is one of the drawback there. So the obvious disadvantage of twice the many diodes, only one disadvantage is there. In the center tap, only 2 diodes are there, but here how many diodes are required? 4 diodes are required. That is one of the disadvantage. But diode cost is very less. It is a more economical. That's why you can go with the bridge rectifier in the practical cases. Okay, this is about all rectifiers concept. I hope that everyone enjoy the class. So next we are moving to the filter concept. Thank you.